Now we'll start here the static theory of failures. So we'll discuss here the static theory of failures for ductile material and the brittle material. And already we have done the concept about the various type of stresses induced in the machine members due to different type of loadings. And the Mohr circle, and particularly we are interested in the three-dimensional Mohr circle, in which we have developed the concept of absolute shear. And one property in a tension test that we have developed is the SYS, which is equal to SYT by 2. Now first of all, we'll try to understand what exactly the failure means. So failure means that whatever the machine part we have, it will break up into pieces. And when we say break up into pieces, it means that the stresses developed in the member will exceed the allowable stresses. In that case, the part will break and we'll say it's a failure. Or because of the forces act, the part is permanently distorted. That will be also called as the failure. When we say the part is permanently distorted, it means that the geometry has been changed. The third failure, we will say that the reliability will downgraded. Then again it will be said as a failure. So before the failure, the machine part has a good reliability, but at failure the reliability is downgraded. And if you design a part for certain functionality, and if that functionality is compromised, then it is also called as failure. So the fourth failure will be the functionally compromised. So these are the four ways we can say failure, but as far as we are considered in the static theory of failure, we'll only consider the first two parts, that is it will break into the pieces and the geometry is permanently changed. That is, it is permanently distorted. Now the static loading means that the load, that is the force and the couple acting on the machine element are stationary. Say for example, we have a shaft here and shaft is supported at the two support, and we have a static loading here that equal to either the force F or may have a certain couple equal to C. Now the magnitude of the force and the couple will not change with respect to time, then it will be called as static loading. Or we can consider here that we have a shaft which one is supported with the help of bearing at the both ends. And suppose this shaft is rotating at a uniform angular speed that equal to omega. So this time the shaft is rotating with a uniform angular speed equal to omega. So omega is a constant value and therefore angular acceleration alpha will be equal to 0. As alpha is defined as the rate of change of angular speed with respect to time, since omega is constant, alpha will be equal to 0. And on this uniform rotating shaft, if the load F is act and this F is a static load, that is does not change in magnitude and direction, then this is also case of static loading. So when the shaft is rotating with a constant uniform rotational speed and the load is remain constant, is also example of static loading. But in this situation, if the direction of the force and the magnitude of the force will change, then it is not a case of static loading, it will become a case of fatigue loading. That we'll discuss later on, the case of fatigue loading. We are only interested in the failure, the part will break into pieces and the part is permanently distorted. That is when the stress in the machine member will exceed the strength. In that case, we have the failure. How to calculate the stress due to bending, due to direct shear, due to torsion? Then we have done the complex loading. So we can develop here the state of a stress and we can convert the two-dimensional state of a stress into three-dimensional state of a stress, and we can calculate the principal stresses and the shear stress. Now the second part here is the strength. The strength, we can have a yield strength, then we have torsional yield strength, ultimate torsional strength, we have ultimate tensile strength, ultimate compression strength. So some symbols I will show you for the strength. The yield strength under the tension will represent by SYT or simply by SY. Ultimate tensile strength will represent as S suffix UT. Similar to SUT, we have SUC, and value of SUC is same as ultimate compressive strength. Normally for ductile material, both values are identical, but in the brittle material, the value of SUC is higher than the value of SUT. Instead of SYS, I will prefer the symbol SSY, which one is called as a torsional yield strength or shear strength. And in the tension test, we have proved that the torsional yield strength, that is the shear strength, will be equal to the yield strength under tension divided by 2. And one final symbol will represent for ultimate torsional shear strength, which is represented by SSU. S stands for torsional, Y for yield, and U for ultimate. And before we proceed for static theory of failures, first some few facts we want to make clear for ductile material and for brittle material. The design of a ductile material are based on the shear strength, that is the value of SSY, which one is the torsional yield strength or simply the shear strength. And under the tension test, we obtain the value of shear strength equal to SYT divided by 2. As far as the ductile material is considered, we have a yield strength under tension, that is the value of SYT is same as the yield strength in compression. These two values are approximately same value in the case of ductile material. And the ductile material is normally fail due to yielding. So if we go beyond the yield point, the material will fail, whereas the brittle materials are limited by their tensile strength, because the criteria used in the brittle material is a fracture, and the tensile strength we can represent either by SUT, ultimate tensile strength, or the yield tensile strength. But for brittle material, the value of SYT is same as equal to SUT, but the value of SUC, that is the ultimate strength in compression, is greater than the ultimate strength in tension. So design of the brittle material is based on the ultimate tensile strength or ultimate compressive strength. But the ultimate compressive strength is always greater than the ultimate tensile strength. So brittle material will fail when we have a fracture, and because of fracture it will break into number of pieces. Like example, glass is a brittle material, so that will fail when it break into number of pieces, whereas the ductile material will fail when the yielding will start. So these are the two criteria we'll use for static theory of failure. There are number of theories are proposed for static failure. The first one is proposed by Rankine, which one is the maximum principal stress theory. Then the second theory is proposed by the Guest or the Tresca, which is also called as the Guest theory or the Tresca theory, which one is normally used in the case of ductile material, is the maximum shear stress theory. Maximum principal strength theory is proposed by the Saint Venant, and the total strain energy per volume is proposed by Haig. And the distortion energy, which is most commonly used in the case of ductile material, is proposed by the von Mises. So all these theory we'll discuss here in detail one by one. We will start with the maximum principal stress theory, which is used for brittle material and is developed by the Rankine. So let's start with the maximum principal stress theory, that is the Rankine theory. This theory was created by W.H.J. Rankine. It states that the failure of any mechanical component subjected to complex state of a stress occurs whenever one of the three principal stresses, that is sigma 1, sigma 2, sigma 3, equals or exceed the strength, that is whenever the maximum tensile stress exceeds the uniaxial tensile strength, or the maximum compressive stress exceeds the uniaxial compressive strength, then the part will fail. So consider here a two-dimensional state of a stress which is subjected to sigma x, the normal stress along the x-axis, shear stress tau xy, and the normal stress along the y direction. Now this value of sigma x, sigma y will be positive if tensile and negative if compression. Value of tau xy will be positive if we are on the right phase and will go to the positive of y direction. From sigma x, tau xy and sigma y, we can calculate the two principal stresses. Suppose we say that sigma a and sigma b are the two principal stresses. Then we can calculate the value of sigma a as well as sigma b is equal to sigma x plus sigma y divided by 2 plus minus under root of sigma x minus sigma y divided by 2 whole thing square, plus we have shear stress tau xy whole square Either the value of sigma A is greater than sigma B and is greater than 0, that is both value are positive, or we have sigma A, sigma B both are less than 0, that is both are negative, or one value is positive and one value is negative. SUT represent here the ultimate tensile strength and SUC represent here the ultimate compressive strength. Once you calculate two principal stresses sigma A and sigma B, right now we don't know which one is a greater value and which one is a minimum value, or whether we are both positive or both negative. So we'll make here a generalized statement. So according to the maximum principal stress theory, we have a positive principal stress should not be greater than the ultimate tensile strength. So any value of sigma A or sigma B should be always less than the value of ultimate tensile strength. So in this case, either we have sigma A or sigma B, both these value must be, if positive, then must be less than equal to SUT. In this case, we can define the factor of safety N, which is equal to strength divided by stress, is given as SUT, that is the ultimate tensile strength, divided by either V of sigma A or V of sigma B. And if both value will come out to be negative, in that case you have to compare the negative principal stress should not be greater than the ultimate compressive strength. So if A is negative and B is negative, we don't know which one is most negative, then you have to take the absolute value of principal stress A or principal stress B, which one is maximum you have to select, and you take the absolute value. This value must be less than the ultimate compressive strength, that equal to SUC. And in that case, we have to calculate the value of factor of safety N is equal to strength. With this time the strength is equal to SUC and divided by stress. So you have to take the absolute value of either sigma A or sigma B. Since here the value of SUT or SUC is always greater than the principal stresses produced in the machine element, so the factor of safety should always be greater than 1. If the factor of safety is less than 1, it means that the material will fail, and if the factor of safety greater than 1, the material is safe or the part is safe. So using the value of SUT and SUC, we'll develop here the stress envelope, and we'll further explore the geometric interpretation of the maximum principal stress theory. So for factor of safety equal to 1, we can develop the envelope, that is a boundary condition in case of maximum principal stress theory. Suppose both the value of sigma A and sigma B are positive value, that is a tensile. In that case, the limiting condition will be equal to sigma A will be same as equal to SUT and sigma B is equal to SUT. So we'll plot here sigma A and sigma B on x and y axis. On x axis we'll plot the value of sigma A. On y axis we'll plot the value of sigma B. So these are represent the tensile stress, that is both of the principal stresses are tensile, and this value represent here the negative value of principal stress sigma B, which one is compression, and this value represent the negative value of sigma A, which one is compression. So in the quadrant 1 here, both the value are tensile, and in quadrant 3 both the value of the principal stress are compression. So if one of the principal stress, that is sigma A, is tensile, then sigma A will be SUT. That can be represented by one vertical line passing through SUT. Now for brittle material, the value of SUC is always greater than the value of SUT. So SUT value will show slightly smaller value. So somewhere I will show the value of SUT. This value I will show as SUT, and the SUC value will show here slightly higher value. So this one is SUC but negative value, and this one is SUC but negative value. So this vertical line represent here the value of sigma A is equal to SUT. And if the second principal stress is also positive, then that you have to take as a SUT. So you have to draw here one horizontal line which represents the value of sigma B is same as equal to SUT. So this dotted line here represent the value of sigma b will be equal to SUT. But if both the stresses are compressive, that is the sigma A is compressive, then you have to compare the modulus of sigma A, that is the absolute value of sigma A must equal to SUC, and the absolute value of second principal stress sigma B will be equal to SUC. If we have a absolute value of sigma A equal to SUC, you have to draw the vertical line through SUC similar to this line. So these dotted lines represent here the absolute value of sigma A is equal to SUC. And one horizontal line will pass through negative of SUC, that will represent the absolute value of sigma B equal to SUC. So this dotted line represent the modulus of sigma B, that is the second principal stress is equal to SUC. So this area is the area which is valid for the maximum principal stress theory, and if the principal stresses value sigma A and sigma B fall within this region, then the part is safe. That is, the design is okay. So anywhere two principal stresses if lie inside this region, which is have a boundary of SUT and SUC, the part is safe. So this region is a safe region, and outside this one we have a fail. So part will fail outside this region. Okay, that is the one part we have done here, that is the fence we have done. So for the fence here, that is a square basically, and the center of the square is shifted. So this one is representing the boundary where the factor of safety is equal to 1. Inside the region the part is safe, and outside the region the part is fail. Question is how to calculate the value of factor of safety if both the principal stresses will lie in the first quadrant. In the first quadrant, sigma A and sigma B both are tensile in nature, whereas in the quadrant 2, the value of sigma B is positive, that is a tensile, and the value of sigma A is negative, that is a compressive. So one stress is positive and one stress is compressive. And in the quadrant 3, both the stresses, that is sigma A and sigma B, are negative. This one is representing the negative value of principal stress B, and this represent the principal stress negative is sigma A. Whereas in quadrant 4, we are in the safe region, that is the value is less than SUT and SUC, part is safe. And here the value of sigma A is tensile in nature and the sigma B is a compressive in nature. So quadrant wise we'll discuss here how to find out the factor of safety. Suppose we are in quadrant 1, the value of sigma A is greater than 0, sigma B greater than 0, and both are tensile in nature. And in the quadrant 1 here, we will find that the boundary is same as equal to SUT. So SUT will decide the value of factor of safety. So in this case, suppose we have the value of sigma A is greater than sigma B. In that case, the sigma A is a larger principal stress, and we can calculate the value of factor of safety N is equal to SUT, that is the strength divided by maximum principal stress. So this time we have sigma A. And if value of sigma B is greater than sigma A, in that case the maximum principal stress is sigma B, and since we have both the limit is SUT, we can calculate the factor of safety N is equal to SUT divided by maximum value of principal stress, that equal to sigma B. So both time here SUT come because both the boundary conditions are represented by SUT. Now first of all we'll go to the quadrant 3 here. In the quadrant 3 both the boundary conditions are SUC, that is the limiting value is SUC, and if the principal stresses if lie in the third quadrant which are lower than the SUC, the part is safe. So in the quadrant 3, sigma A less than 0, sigma B less than 0, that is both the principal stresses are negative, that is the compressive nature. So you have to compare their magnitude, so you have to take the absolute value. This time the boundary condition is decided by SUC, so there are the two possible chances, either the absolute value of A greater than sigma B. So if we have absolute value of principal stress A is greater than absolute value of principal stress B, Then we have factor of safety. Since it's a compressive, limiting condition is SUC, so we have strength is equal to SUC divided by the larger principal stress magnitude wise is principal stress A. And if maximum principal stress sigma B magnitude wise is greater than the second principal stress sigma A, in that case we have to calculate the factor of safety again based on SUC. So we have SUC divided by the larger principal stress equal to sigma B. So here there is no issue in quadrant 1 and quadrant 3. So either this is true or this is true, and what is true is depend upon which one is a larger principal stress. But as far as the quadrant 2 is considered and the quadrant 4 is considered, one of the principal stress is positive and the other principal stress is negative. So in that case you have to calculate here, if the principal stress is positive then you have to compare with SUT, and if the principal stress is negative you have to compare with SUC. So in this case for quadrant 2 and quadrant 4 you have to calculate the two factor of safety. Why we have to calculate two factor of safety? Because for quadrant 2 one limit is SUT and other limit is SUC, as well as for quadrant 4 one limit is SUT and other is SUC, whereas for quadrant 1 and quadrant 2 you have to calculate one factor of safety based on the larger value of the principal stress, because both the limit are SUT or both the limit are SUC. So consider here quadrant 2. For quadrant 2, the value of principal stress sigma A is negative, that is a compressive in nature. So you have to compare with the absolute value of the sigma A with SUC, and sigma B is a positive value. So you have to compare the sigma B with SUT. In this fashion, we can calculate here the two values of the factor of safety. So N1 is a factor of safety based on the compressive stress sigma A. So we have compressive stress, so you have to take the ultimate value of the compressive stress in compression divided by absolute value of principal stress sigma A. And then you have to calculate the second factor of safety N2, which is based on the tensile stress sigma B. So this time the strength is taken as SUT divided by, this value is already positive, so you have to divide it by sigma B. Now once you find out the value of N1 and N2, then you have to select the minimum value. So you have to select here the minimum of N1 and N2. And now we are in quadrant 4. For quadrant 4, the principal stress sigma A is positive and the other principal stress sigma B is compressive. So sigma A is greater than 0, that is a tensile, and sigma B less than 0, that is a compressive. For this situation also you have to calculate the two factor of safety. N1 value this time will be with respect to the sigma A value, and sigma A is positive value and it's a tensile, so you have to compare the tensile with SUT. So we have SUT divided by sigma A. And the second value of factor of safety you have to calculate based on sigma B, which one is compressive. So N2, since it's a compressive, you have to compare with SUC divided by, since it's a negative value, so we'll take the modulus as sigma B. Again you have to select the minimum of N1, N2 of the two factor of safety N1 and N2. In this fashion we can calculate the factor of safety in the case of maximum principal stress theory, that is the Rankine theory. The problem is here only with the second quadrant and the fourth quadrant. As far as the first quadrant, third quadrant, we have to first select the largest principal stress, either sigma A, sigma B, and compare with SUT. As far as the quadrant 3 is considered, you have to select the largest principal stress. For that one, you have to find out the absolute value of sigma A, absolute value of sigma B, and you have to compare that value with SUC. In the quadrant 2, you have to calculate the two factor of safety, one based on SUC and one based on SUT. Same story repeat for quadrant 4 also. So we'll take some example here and we'll try to get the concept more clear how to calculate the factor of safety. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.